Let's start with our first paper of electric potential and capacitance. So question number 1 says if 400 joules of work is done in moving an electric charge, okay, of 4 coulombs. So let me first write what is given here. Work done. Work done is our potential energy, if you remember, that is 400 joules. In moving an electric charge here is Q equals to 4 coulomb from a place of 10 volt. So V1 is 10 volt to another place of volt V. So V2 is V volt. Okay. We have to find the value of V. So we should know that work done is nothing but potential energy, which is equals to charge into potential difference. Okay. So potential difference VAB or V12 you can say. So while going from first place to second place, right? So here we will put here work done is 400 joules and that is equals to charge, which is 4 coulomb, and while going from 1 to 2 potential difference will be V minus 10. Be very careful. V2 minus V1 it will be. Taking 4 on the left hand side it will be 100 and that will be equals to V minus 10, correct? And 10 goes on the left hand side, it becomes 110, which is equals to V. So our voltage V2 will be 110 volt, which is option B. Let's move to question number 2. Question number 2 says if 100 joules of work done in moving a charge of 25 coulomb across a path having potential difference VAB, the value of VAB they are asking straight away. Okay. So direct formula, work done will be equals to charge, okay, into potential difference VAB straight away. So work done is 100 joules as per the question and 25 coulomb is the charge. So VAB straight away will be VAB. No need of doing VB minus VA because they are asking VAB only. Taking 25 on the other side, it will be 4 volt, which will be equals to VAB. So correct answer is 4 volt, option A for question number 2. Let's do the question number 3. Question number 3 says the work done in taking an electron around the nucleus of a hydrogen atom. Okay. Now there are two reasons for this particular problem. First reason is our electric field is a conservative field. What is a conservative field? Okay, conservative field. What is a conservative field? Conservative field is the one which is associated with a conservative force. What is a conservative force? A force which is independent of the path. Okay, it only depends on initial and final location. Okay, and the net work done around any conservative field or force is 0. Right? Okay, if it is coming back to initial position. One reason. Second reason will be our initial position and final position is same, so displacement is 0. So work done will be 0. So work done or potential energy of such a system is 0 joules. Option A. Both the reasons are fine. Let's move to question number 4. Question 4 says electric field intensity at a point B due to a point charge Q. So this is our point B, let's say, and kept at a charge at a point A. So charge is how much? Q. Separation between AB is, let's say, L or R. You can take according to your choice. The electric field here is 24 Newton per coulomb and potential here is 12 joules per coulomb. Now we know the relation between electric field and potential is E into L is equals to V. So L is equals to V by E. And what is the voltage here? 12. And what's the electric field? 24. So 1 by 2. 1 by 2 is nothing but 0.5 meters. So correct answer is option C. I hope this is clear. This is our question number 4. Let's move to question number 5. Question 5 says, quite similar to the fourth one, electric field intensity at point B, again, due to the same charge at A, Q, and the electric field here is how much? 24 newtons per coulomb. And what is the voltage? 12 joules per coulomb. So what will be the separation now? L is equals to V by E, correct? L is the separation. We need to find separation to find the magnitude of charge. In this question, they are asking the charge. So voltage is how much? 12. Electric field is how much? 24. So this is 0.5 meter. Now once you found the V, let's find the charge. How will you find? V equals to KQ by L. Correct? KQ by R or L doesn't make any difference. So Q will be equals to V into L upon K. Now what is the voltage? 12 into length 0.5 whole divided by 9 into 10 to the power 9. This will give you 6 by 9 into 10 to the power minus 9. And making it 3 2s and 3 3s into 10 to the power minus 9. So that is nearly 0.6 into 10 to the power minus 9 coulomb. Let's see if there is any option. Yes, option A is correct. 0.66 into 10 raised to minus 9 coulomb. That's the charge at A. Let's move to question number 6 now. Okay, so question number 6 here is a charge of 24 microcoulomb. Charge here is Q is equals to 24 microcoulomb wins 10 to the power minus 6 coulombs. Is given to a hollow metallic sphere of radii 0.2 meter. So radii here is 0.2 meter. We have to find the potential on the surface of the sphere. So potential is nothing but kq by r. K here is 9 into 10 to the power 9. Charge here is 24 into 10 to the power minus 6 and r is nothing but 0.2. Let's remove this point. We will get here 10. 2 cancels with 12. Okay, 24 as 12. And this will give you 9 2s are 18, 108 into 10 to the power 3 into 10. So we can make it as 108 into 10 to the power 4. Now we have here in decimal, so 1.08 into 10 to the power 6 volt, that is option B. So correct answer for question 6 is option B. Let's move to 7th one. Question number 7 says a charge of 10 nanocoulomb. So Q here is 10 nanocoulomb, 10 into 10 to the power minus 9 coulomb, is given to a hollow metallic sphere of radii 9 meters. The potential, the same similar question. So again kq by r. K here is 9 into 10 to the power 9. Q here is 10 into 10 to the power minus 9 whole divided by 9. So let's cancel out the terms. 9 cancels with 9 and you're left with 10 volts. That's option A. Correct it is. That's our question number 7 in practice paper 1. Let's move to question number 8. If a charge of 20 nanocoulombs is given to a metallic sphere and this produces 90 volt. Be careful, voltage is given. We have to find the R. So V will be equals to kq by R and R will be equals to kq by V. And what is K here? 9 into 10 to the power 9 and charge 20 into 10 to the power minus 9 whole divided by voltage. What is voltage? 90. Let's cancel out this with this and 9 with this. We're left with 2 meters. Correct answer is option B, 2 meters. Let's move to question number 9. Question number 9 says, if the voltage produced by a sphere, metallic sphere, at a distance r is equals to 9 meter, voltage is 20 meters, the charge we have to find. Correct? So V will be equals to kq by r. Let's take everything on the other side. So V into r upon k, that will be q. So here let's substitute the value of V, which is 20, R is 9 and K is 9 into 10 to the power 9 equals Q. Let's cancel this 9 with 9. We left with 20 into 10 to the power minus 9 coulomb, that is Q. So 20 nanocoulombs it will be. And we can also rewrite it as 2 into 10 to the power minus 8 coulomb. That is option A. Option A is correct for question number 9. Let's move to question number 10. Question number 10 says, the amount of work done in bringing a charge of 2 into 10 to the power minus 9 from infinity to a point P must be. So, work done will be stored as the potential energy and that will be K Q1 Q2 by R. And infinity, when you will consider, 1 by infinity is 0, so we can skip that part. Okay, we will directly substitute the values. 9 into 10 to the power 9. Charge, if it is not infinity, you have to consider that point. So 9 into 10 to the power 9. Q1, what is the first charge? Okay, Q is 4 into 10 to the power minus 7. This is the source charge and test charge we are getting is 2 into 10 to the power minus 9. Okay, whole divided by at what point we are getting 9. So let's cancel out this 9 with 9 and we left with 4 2s are 8 into 10 to the power minus 7. Okay, minus 7, 9 and this 10 to the power minus 9 cancels, so 8 into 10 to the power minus 7 joules. Okay, this is our correct answer. So 8 into 10 to the power minus 7, that's our option. Is there any option? No. So correct answer is option D, none. Okay, that is the amount of work we have to do. This was paper 1.